We now have this new thing called magnetism, and the first thing to realize is that it's not the same as electric fields. A magnetic field and an electric field are not the same. Okay, we've all seen a bar magnet, right? And we've all seen a compass. Let me see if I can actually project this. And a compass needle points in what direction? North. Points north along north-south. So here is a compass. And here's a bar magnet, and I bring one end of this bar magnet nearby, and it seems like it's attracting one end of the compass. And I flip it, and it seems like it's attracting the other end of the compass. And I say, well, maybe that's just some sort of static electric charge on this little piece of metal here. It's maybe polarized somehow, and it's affecting this. Well, that's possible, but I could. Not going to go through it, but I could disprove it by saying, if I brought a charged piece of tape, for example, near this thing, might be able to get it to attract the needle, but it would attract either end of the needle. Okay, there wouldn't be a dependence, right? There would be, okay, if you brought it near this end, it would polarize it and attract it. If you brought it near the other end, it would polarize it and attract it. So it's different, right? Or if I brought a charged tape near one end of the compass, I'd see attraction to both ends, okay? So I wouldn't see repulsion from one end, meaning it's not just static charge on the ends of a bar magnet, okay? Another thing that's kind of different about magnetism is, and here's a simple little circuit, okay? I've got two batteries hooked up together to a light bulb, and if I connect the circuit, lo and behold, the light bulb lights up. If I bring let me disconnect it for a second. I bring the wire nearby, wire of this battery, the circuit nearby, and nothing happens, okay? I connect the circuit together, and I bring the wire nearby. You see that? It's kind of deflect. If I move it away, it kind of goes back to where it was. Maybe if I kill the lights, it would help. Move it away, and it kind of points, the needle is pointing north, something like that, right? Bring the wire nearby, and the needle is deflected. And if I change the direction of the wire here, the needle is deflected the other direction. And if I disconnect the circuit, it goes back to where it was. That's different too. Right? We can't just explain that with static charges because there really is there's at least very little static charge, and the key idea here is that when you have a circuit, what's going on with the charges inside? Electrons inside the wire are doing what? They're moving. Okay, so you have moving charges that are somehow affecting this compass, which is essentially a bar magnet. So magnetic fields have to do with moving charges. The key idea behind a compass is that the needle points in the direction of the net magnetic field at that particular location. Okay, so we can use the compass as a magnetic field detector. We don't know how it works yet, but we can just say, okay, compass needle is going to point in the direction of the net magnetic field at that location. Well, the Earth is a bar magnet, and we'll talk more about that later. But the Earth makes its own magnetic field, and we've known for centuries that it points north, right? That's where this all comes from. So if you have just the magnetic field due to the Earth, your compass needle is going to point north. But now, we don't just have the magnetic field due to the Earth, right? North is that way, so we've carefully laid out this wire to be in the same direction as north-south. North is that way on this picture. Conventional current's running the other way. Conventional current's going south. And we placed a compass directly underneath the wire. Okay, so we're looking, it's a top-down view. Here's the wire, and below the compass, or below the wire is the compass. What way is the needle going to point? Think about it. Talk it over. Lots of different answers. So we have, some people were also going to be pointing in direction 1. Some people were saying direction 8, so deflected sort of the same way, but not quite as much. We have another large vote for the other direction, 6, and then a smattering of things in between. Well, what do you have to think about? What do we need to know? How many sources of magnetic field are there? 2. There's actually 2, and we have to use superposition to deal with that, right? So let's forget the wire for just a second. If I just had the compass and no wire, the magnetic field is just going to be due to the Earth, and so the needle should point that way. All right. So this is the magnetic field due to the Earth, and that's going to be true no matter what. Okay? We can treat that as, when we use superposition, we can say, again, the field due to one thing is independent of the other thing. We just have to add them up. And so now I've placed a wire on top, and I is running that way. Where's the observation location with respect to the wire? Underneath it, right? So the r hat vector is pointing that way, right? So point the fingers in the direction of I, curl them towards the observation location, which is that way, and underneath the wire the thumb points up, right? So now I have the magnetic field of the Earth pointing in that direction. Let me redraw it over here. B of the Earth pointing in that direction. B of the wire pointing in that direction underneath the wire. And so when I add those two together, the net magnetic field should point in a direction close to 8, right? Now, of course, it's going to depend on the relative magnitude. If you could, in fact, have a very large magnetic field due to the wire, and it might get very close to looking like a 90-degree deflection. It might get very close to direction 1, but it's not going to ever be exactly direction 1 because you're always going to have this field due to the Earth. And if the current is not as large, it's going to be somewhere in between. So we have something like that. Okay, that's B net. Now this magnetic field to the Earth is really the horizontal component. What that means is if you were to actually measure the magnetic field due to the Earth at some location here, there'd be a component pointing north. There'd also be a vertical component. There's a fairly sizable component pointing down in towards the Earth. So we're really just looking at the horizontal component here. And compasses are built to be counterbalanced so they can compensate for the field pointing inward. And they're just looking at the horizontal component. The horizontal component of the magnetic field due to the Earth in our neck of the woods, it changes, of course, depending on where you are on the Earth. But in most of the continental U.S., it's about 2 times 10 to the minus 5 Tesla. Okay, so that's just a good number to keep in mind as a reference. And then we can actually use that result to calculate a magnetic field. So let's skip ahead here. Let's say, okay, so we've rearranged the same sort of situation. You have a wire on top of a compass, and you're running a current through the wire. And without the current, the compass needle would point north, but with the current, it's deflected by an angle theta, 12 degrees to the west. You know the horizontal component is 2 times 10 to the minus 5 Tesla. What's going to be the magnitude of the magnetic field made by the current, by the moving electrons on the wire? Let's see if you can figure this out. So I'll redraw it here. That's the direction of the net magnetic field. Okay. B of the Earth is this way. This is 12 degrees. And you know B of the Earth is 2 times 10 to the minus 5 Tesla. So the question is, what's the magnitude of the field due to the wire, magnetic field due to the wire? Okay, and so we're all over the map. So we do need a little review of trigonometry. This is the magnetic field of the Earth, right? What do we know about the direction of the magnetic field due to the wire? It's the same situation as before, right? So it's pointing that way. Yeah, it's pointing that way. So that's B of the wire. And this is a right triangle, right? So that component, the B of the wire, is perpendicular to the B of the Earth because we've nicely laid the wire out running north-south to give us a magnetic field perpendicular to the magnetic field of the Earth. So here's the angle, 12 degrees. Well, I know the adjacent side. I'm looking for the opposite side. What trig function do I want? Tangent, right? Tangent of theta is going to give me the opposite B of the wire over the adjacent B of the Earth. And then I can just solve for it. So we have 2 times 10 to the minus 5 times the tangent of 12 degrees. What's that give us? Is it 4.3? What's it work out to be? Is it answer 4? Is it really answer 4? Yeah, okay, 4.3 times 10 to the minus 6. Okay? Everybody okay here? Questions? So this is useful for, we have not only a magnetic field detector, we have a way to measure it. Okay, one thing before you go. I'm just going to give you a result that you're going to need for homeworks. And we may come back to the derivation next time if there's time. So we showed the numerical result for the magnetic field of the long wire. Okay, you could work it out analytically and calculate using an integral what the result would be for the magnetic field that has a length L. So we're running from negative L, x equal negative L over 2 to x equal positive L over 2. Conventional current I. Here's a little length delta L, and that's R, and this is some location 0, Y, 0, and this is location X, 0, 0, okay? What you'd have to do is figure out delta B is equal to mu naught over 4 pi, delta L cross R hat over R squared, and then write R and delta L in terms of the known quantities, namely X, Y, and the current. Okay, this is laid out in the book. You then sum up all those delta B's, which means you are then doing an integral of the dB's. You get a result for the magnetic field of a wire of length L along that center line axis, and this is the result. The result is mu naught over 4 pi, and this is just a magnitude now, not a direction. Mu naught over 4 pi, capital L times I over R times square root of R squared plus L over 2 squared, where I'm really now calling this distance R, just like we have done in the past. I'm changing the name of that Y to R, meaning the perpendicular distance away from the current. One approximation that's useful is when you have a very long wire. L is much bigger than R. If you simplify it, you'll find that the magnetic field of the wire, long wire, is equal to mu naught over 4 pi 2I over R. So you get a 1 over R distance dependence for a very long, thin wire, just like we got a 1 over R distance dependence for the electric field of a long, thin, charged rod. Okay, so the geometry is kind of similar. But we have a nice formula for the magnitude. The direction then would come from the right-hand rule, and you should be able to then predict what the vector would be at a particular location.